The world is constantly changing. Technology continues to develop, especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent technologies, CT scan has transformed into a very useful imaging modality. Images produced by CT are able to provide an accurate detailed look at the patient's organs in a short time, supporting accurate diagnosis. Image quality is a vital aspect that must be achieved in CT examinations. Research on CT scans continues to grow rapidly. Researchers continuously innovate to give their best contribution to society. All efforts are made to improve the effectiveness of the health services. One of the results of this innovative research is IndoQCT. IndoQCT is a software to automatically evaluate the quality of CT image. IndoQCT can be downloaded on the website www.IndoQCT.com. IndoQCT is able to measure various image parameters from a variety of phantoms available on the market. Measurements with IndoQCT are carried out quickly and accurately. With only a click, the calculation is carried out automatically without much intervention from the user. IndoQCT has three main objectives. First, it's a tool for medical physicists to effectively and quickly accomplish their task in routine quality control of CT. Second, it's a scientific tool for CT scan research. And third, IndoQCT is a tool for educational purposes, especially education regarding the quality of CT images. Unlike previously available software which were limited to certain parameters and phantoms, IndoQCT is capable of measuring various parameters from a variety of available phantoms, such as the AAPM CT Performance Phantom, the ACR CT Accreditation Phantom, the CAPFAN Phantom, the GE CTQF Phantom, the Canon TOS Phantom, the Philips CTQF Phantom, the Siemens CT Phantom, the Newsoft CT Phantom, and the Anthropomorphic Phantom. IndoQCT can also generate synthetic images using a computational approach called the computational phantom, which is useful for educational purposes. The main capabilities of IndoQCT are to measure CT number, noise, spatial resolution, slice thickness, low contrast detectability, alignment, gantry tilt, distance, and distance between slices. IndoQCT is also reliable in measuring image quality metrics directly from patient images. It's advantageous for simplifying and increasing the objectivity of the dose optimization process.
Cek. Udah.
IndoQCT is also equipped with several additional features, including texture analysis, some noise reduction, several windowing options, including multiple windows blending in the form of red, green, blue images. And image reformatting on sagittal, coronal, oblique, and irregular planes. IndoQCT will be able to connect the picture archiving and communication systems to facilitate user in collecting images directly from DICOM servers. It doesn't stop there. With IndoQCT, you can store, measure data to an integrated database. This storage has been facilitated with an export tool to save data in Microsoft Excel document format. IndoQCT provides convenience in the aspect of efficiency, measurement objectivity, universality, and portability. Many international publications have been produced using this software. Research opportunities with IndoQCT are ongoing so that the number of research projects using IndoQCT will continue to rise. The world is constantly changing. Technology continues to develop, especially medical technology. Researchers are constantly innovating to ensure the highest quality of health for humans. Among recent technologies, CT scan has transformed into a very useful imaging modality. Images produced by CT are able to provide an accurate detailed look at the patient's organs in a short time. Supporting accurate diagnosis, image quality is a vital aspect that must be achieved in CT examinations. Research on CT scans continues to grow rapidly. Researchers continuously innovate to give their best contribution to society. All efforts are made to improve the effectiveness of the health services. One of the results of this innovative research is IndoQCT. IndoQCT is a software to automatically evaluate the quality of CT image. IndoQCT can be downloaded on the website www.indocct.com. IndoQCT is able to measure various image parameters from a variety of phantoms available on the market. Measurements with IndoQCT are carried out quickly and accurately. With only a click, the calculation is carried out automatically without much intervention from the user. IndoQCT has three main objectives. First, it's a tool for medical physicists to effectively and quickly accomplish their task in routine quality control of CT. Second, it's a scientific tool for CT scan research. And third, IndoQCT is a tool for educational purposes, especially education regarding the quality of CT images. Unlike previously available software which were limited to certain parameters and phantoms, IndoQCT is capable of measuring various parameters from a variety of available phantoms, such as the AAPM CT Performance Phantom, the ACR CT Accreditation Phantom, the CAPFAN Phantom, the GE CTQF Phantom, the Canon TOS Phantom, the Philips CTQF Phantom, the Siemens CT Phantom, the Newsoft CT Phantom, and the Anthropomorphic Phantom. IndoQCT can also generate synthetic images using a computational approach called the computational phantom, which is useful for educational purposes. The main capabilities of IndoQCT are to measure CT number, noise, spatial resolution,
Assalamualaikum warahmatullahi wabarakatuh. Hello, good morning everyone. Welcome to the fourth day of summer course in Medical Physics 2025. With the title IndoQCT for CT Image Quality Measurements. In this fourth day, we will have a session with Dr. Khairul Anam regarding to the topic we have talked yesterday. We will have a lecture in the theme of noise, NPS, noise uniformity, and its measurement. Okay, let's greet our lecturer first, Dr. Khairul Anam. Can you join us?
Yeah.
Good morning, Doctor.
Morning.
Okay. Okay, everyone. Without any further ado, we can start the lecture today with Dr. Khairul Anam. So please, Dr. Khairul Anam, to start the lecture.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning. And
Good
today
morning,
is the
Dr.
fourth
Agus.
day of our summer course. And now we will learn about the noise and noise quality, NPS, and also measurements using IndoQCT. This is the table of content of today's summer course. Introduction, noise measurement, and then noise uniformity measurement, noise homogeneity measurement, NPS measurement, and conclusion. And after that, we will try together to measure many parameters of noise using IndoQCT. Okay, this is the basic one. The noise is I think, is the most important parameters of image quality. The noise is stochastic fluctuation of pixel values like this due to measurement uncertainty, such as the quantum noise or imperfectness of the imaging system like this. This is the ideal image with the low noise. This example of the medium noise within the image, and this is the example of the high noise. And the fluctuation due to anatomical variation are not considered as noise. Okay, the noise come from three main categories: the quantum noise, image generation process noise, and system limitation. We will discuss the noise, the quantum noise. The quantum noise is the noise related to the number of the photon. It means that if the number of photon become bigger, then the noise become lower. And several parameters affecting the quantum noise, such as the tube current, tube voltage, scan speed, slice thickness, pitch, and so on. Tube current, for example, if the tube current small, so the photon is very small also. And the small number of photon will lead to the very noisy of the image. Conversely, if the tube current is high, so the number of photon is high, so the noise will be lower. It is the quantum noise related to the number of the photon. Also from the slice thickness, if the slice thickness become thicker, so the number of photon come to the detector will be higher, so the noise will be lower. So the quantum noise is related to the number of the photon. Okay. This is the example of the two images with different noise. Top example, the noise is relatively lower, and in the bottom image, the noise is relatively higher. We can see here the appearance of the two images with different level of the noises. Okay, now we will see the impact of the MAS or tube loading and slice thickness on the noise. As I already mentioned, the x-axis is the MAS or tube loading, and the y-axis is the noise square. And we can see here, if the MAS increase, meaning that the number of photon increase, so the noise will decrease. And in this example, slice thickness, if the slice thickness is thicker, increase, so the photon reach in the detector will increase. And in the result, the noise will decrease like this. This is the example of the effect of MES and slice thickness on the noise. And now the second source of the noise is noise from the image generating process. For example, from the image reconstruction and the calibration effectiveness. The parameters of reconstruction, if for example we use the filter back projection, we have the many filters or kernel. Every kernel has specific method and will lead to the different noise level. For example, the lung filter, Boone filter, and so on. They have a specific type and specific noise level. Also, the reconstruction type, for example, the IR, filter back projection, or deep learning image reconstruction, they have the different level of the noise. Also the calibration effectiveness. So the noise from image generation process produced in the noise. This is the example of the image reconstructed with the three different kernel, soft kernel, Boone kernel, and the edge kernel. We can see here that the image is different. The noise in the edge kernel is very high, and for the soft kernel, the noise is very low. So the kernel will affect to the noise level in the image. This is another example. We have two images in the top and the bottom. In the top is the filtered with the filter back projection, and in the bottom is image reconstructed using IR, VO. And we can see that the noise is different. Using filter back projection, the image is noisy, and by using VO, the noise is less. And we can see in the left and the right side of the images, and in the left is with reconstructed with the very small slice thickness, and in the right is reconstructed with 5 millimeters. And if we see these two images, the noise level is different. And the number three, the source of the noise is the noise from system limitation. For example, from the electronic system, and noise from the data acquisition, noise from the scatter radiation, and so on. Yeah, we know that our system is not so perfect, and imperfectness of our system produce the noise. This is the example, the paper written by Duan, the electronic noise. This one is the example of the noise reconstructed and scanned with the two different detector, using the conventional detector and using the integrated detector. And we can see here that the noise is different. Using the integrated detector, the noise is lower compared to the conventional one for every tube current. So this is the noise from the system limitation. So the noise can be avoided. The noise only can be mitigated, but we cannot avoid the noise at all. The noise still exists in the image. And now we move to the second top, the noise measurement. The easiest way to characterize the noise is by measuring the standard deviation. As we already mentioned, that the noise is the fluctuation in the pixel within the image. So the very easiest way is to measure the standard deviation using this formula. And then we made the ROI contain many pixel values within it, and then we calculate the standard deviation. So this standard deviation is considered as the noise level, and it is very easy, and we can measure it using many softwares. Okay, this is the more detailed explanation about the measuring noise. We create a ROI here, and within the ROI there are many pixels. In every pixel we have so many different values with the fluctuation values, and then we calculate the standard deviation using this formula, and eventually we have the 0.63 Hounsfield unit. This is the example of the noise within this ROI. And for measuring the noise, we should have phantoms, or we can also measure on the patient images. But for easiest way, we use the phantom. And we use the homogeneous phantom. As already mentioned, this is the example of the three homogeneous images from the three phantom. This one is from AAPM phantom, OCR phantom, and CAT-FAN phantom. And also we can use the phantom from our vendors, GE, Siemens, Philips, and so on. And then we look at the ROI in the homogeneous region. And regarding the size of the ROI, it is not so small and not so wide, because if the ROI is so small, may not provide reliable statistic. But conversely, if the noise so wide, may capture anatomical variation. So we use the standard noise size. AAPM said that the ROI must be around 1 centimeter square, or its diameter, it's around 10% of the phantom diameter. It is not phantom area, but phantom diameter. And this is our study I have shown to you yesterday. This is our study to investigate the impact of the ROI size on the noise. We can see here, if the ROI is so small, the fluctuation of measurement exists here. But if the ROI become wider, the more stable result will be achieved like this. At least around 25 pixels, it is enough for measuring the noise. But I suggest, as the AAPM suggests, by using the ROI around its diameter, it's around 10% of the diameter of the image. This is the standard from the IAEA, from the image noise. ABM said that image noise should be within 10% of baseline for achievable criteria. And for the acceptable criteria, the noise should be within 25% of the baseline. Okay. Of course, we can measure the noise using the IndoQCT. We can measure either manually and automatically, and we will try together after I explain this PPT. And now we move to the noise uniformity measurement. As in the city number, the noise also in different location may be different. So it is important for us to measure the noise uniformity. For measuring noise uniformity, similar to to measure the image Hounsfield unit city number consistency, We use the 5 ROIs with diameter around 10% of the diameter of the phantom and should be placed at the center at the 12, 3, 6, and 9 o'clock. And for the peripheral ROIs should be placed approximately 1 ROI diameter away from the phantom border. And then we calculate the noise magnitude by its standard deviation within each ROI. In Indonesia, the noise uniformity basically very easy to calculate. If we have the noise from the 5 ROIs, and then we identify the maximum one and we identify the minimum one, and then we subtract the maximum with the minimum noise, and we will have the noise uniformity. In Indonesia, we should normalize our noise measurement with the tube voltage of 120 kilovolt peak, tube loading of 300 milliampere second, and slice thickness of the 8 millimeters. Sometimes we measure the image noise, we scan with the different values. So we should this formula to normalize, to make the normalization of our measurement using this formula. This is our noise measurement, sigma m, and this is our tube voltage for scanning, and this is our tube loading for scanning, and this is our slice thickness, slice width for measurement. And then by using this formula, we have the noise normalization. And for measuring the noise uniformity, we use this noise normalization. We identify the maximum and we identify the minimum, and by using this formula, we will have the noise uniformity. In Indonesia, the noise uniformity should be less than 2 Hounsfield unit for passing criteria. And of course, as usual, we can measure the noise uniformity using IndoQCT. This is our result, our measurement, and this one our estimation. Our estimation using 120 kilovolt peak, 300 milliampere second, and slice thickness of 8 millimeters. So the IndoQCT will identify our slice thickness, our kilovolt tube voltage, our tube loading from the DICOM info. And then the IndoQCT will calculate the noise uniformity. This is the result, and we can compare with the standard here. Okay, now we move to the noise homogeneity measurement. Okay, as I already mentioned yesterday, that uniformity may not enough for characterizing the differences of the city number or noise within the image. So we need more sensitive parameters. In this occasion, we can use the homogeneity, the city number homogeneity, or and in this example, we can use the noise homogeneity. Okay, for measuring the city number homogeneity, the first step, we should create the noise map. And this is example the image, and then we have the kernel size. In this example, 3 by 3, and of course you can change the kernel size, maybe 9 by 9, and in specific location we calculate the SD by using this formula, and then we move 1 pixel to the right, and we calculate again the SD in this location, and then we move again 1 pixel to the right, and we calculate again, and we have the SD here, and continue to all pixels, and then we have this type of the SD map. This is example of SD map. From this SD map, we can measure many parameters. One of them is the global noise index, or GNI. Okay, if we develop the histogram from this SD map, we will have this histogram. We can see here in this histogram, the x-axis is the SD, and the y-axis is the frequency. In the maximum frequency, the SD in the maximum frequency is considered as the global noise index, indicating the noise within the image. Beside the global noise index, we can also obtain many other parameters. For example, the noise homogeneity. Okay, for measuring the noise homogeneity, we should create the cell like this with the specific size like this, as in the measurement of the city number homogeneity. And then we calculate the average within each cell, and we identify the maximum value, average value, and then we identify the minimum average values, and then we calculate by using this formula the maximum one minus by the minimum one, and we have the noise uniformity, noise homogeneity. Or we can also calculate again from this cell. The first one, we calculate the average in every cell, and then by using this formula, we calculate the standard deviation again within the each cell, and then we will have the NUI, noise uniformity index. This formula is from the report AAPM 233. Okay, yeah, so by using this SD map, minimum we have 3 parameters: global noise index, noise homogeneity, and noise uniformity index, like this. By using the IndoQCT, we can measure these 3 parameters automatically or manually. This one is the GNI, global noise index. This one is NUI, noise uniformity index, and this one is the noise in homogeneity. Okay, like this. And now we move to the last parameters in the noise, is the NPS, noise power spectrum. If we see these 2 images, and this one, we can see that the appearance of the 2 images is different, right? But if we measure, the standard deviation will be same. So the noise of these images is same, but the appearance totally different. So it is not enough to characterize the noise only with the standard deviation. And what is the difference between the 2 images? The difference is the texture. In the left one, with the finer grain, and in the right with the greater coarse grain. Okay, like this. So the difference in the 2 images is not on the noise, but in the frequency of the noise. So the texture will be different. Okay. The noise texture is the visual impression of the image noise, fine or coarse, and the noise texture has large impact on the perceived quality of the city image, and it can be quantitatively characterized by using the noise power spectrum. Okay, so the noise power spectrum or NPS provide more complete description of the noise, not only the magnitude but also the frequency of the noise. In the standard image reconstruction filter back projection, the frequency in every noise is similar, but in the iterative reconstruction, if especially in the uh, deep learning reconstruction, the noise structure has taken an increased importance in the clinical city. So with the emerging of the IR or DLIR in the clinical setting, so it is important to us to measure not only the noise level but also the NPS, noise power spectrum. This is the conceptual the concept of the NPS. For example, if we see the surface of the ocean, we will see the water. We have the wave. Okay. And if we see carefully, the wave is like this. Okay. In the with the very low frequency, we have the tides. In bahasa is the pasang surut. Maybe in the morning is the level of the sea is low, but in the midday the level of sea is high with the very low frequency. The frequency may be around 6 hours. This is tide. And within the image, we have also the sets of wave. And every wave, there is also the small wave like this. So in this example, we have 3 different frequencies. The frequency of the tide, frequency of the set wave, and frequency of the wave itself. So, but in the time domain, it is difficult to see the frequency. But by using the mathematical equation, we can convert from the time domain to the frequency domain. And we will have like this. The x-axis is the frequency. In the y-axis is the amplitude of the wave, like this. So we can see here, there are 3 groups of the frequency: the tide with very low frequency, the set wave with the medium frequency, and the high frequency for the wave. So this one is considered as the noise power spectrum. But in this example is the amplitude. So in the NPS like this. So in the x-axis is frequency, and in the y-axis is the noise power. So we can see the noise in every frequency. So like this. This is the NPS, noise power spectrum. This is another example from the book written by Professor Hesia. We have the 3 images, and these 3 images have same noise level, but with different frequency. This one with the very low frequency, this one with the medium frequency, and this one with the high frequency. Even the appearance is different, but the noise level is same. So by using the NPS, we can characterize these differences. This is the NPS in 2 dimensions. Okay, and this 2 dimension NPS can be converted into 1 dimension, for it is easier to see the frequency of the noise. And now, how to measure the NPS? Okay, to measure the NPS, the first one we should have the phantom. For example, in this example is the cat phantom, and then we scan the phantom, and then we have the image in the homogeneous module, and then we create the ROI. This is the ROI like this. After that, we have the ROI in the 2 dimension, and then we do the fast Fourier transform in 1 dimension. Okay. If we in this example we have only one ROI. For example, we can use the 3 ROI, 5 ROI, 9 ROI, and so on. So if we use the many ROI, then we add all NPS, and then we divide it by the n. N is the number of the ROI. And then we calculate with the delta x, delta y. It is the size of the pixel, and Lx, Lj is the size of the ROI. Maybe our image has the trend. Maybe because of the, for example, the beam hardening effect. So we can delete the effect by using these parameters. It's the detrending. We can use, for example, the mean values within the image, or using the first polynomial order, or using second polynomial order. So the trend within the ROI is deleted. We only fluctuation in the ROI, and then we do the Fourier transformation in 2 dimensions. This is the example of the 2 dimension NPS. And after that, after we have the 2 dimension of NPS, we can convert to the 1 dimension NPS by using the radial averaging. So we have the profile, and then the profile is rotated. So we have many profile, and then we average the NPS. This is the example of the 1 dimension NPS, and we can see here the y-axis is the NPS, noise power spectrum. The unit is the Hounsfield unit square, millimeter square, and the x-axis is the spatial frequency. And we can see here the maximum frequency here. And we can also measure the mean frequency, the average frequency. Okay. This is in this example, we use the 5 ROIs, and this one is the average of the 2 dimension NPS, and this one is the example of the 1 dimension NPS, and we can calculate the peak frequency, and we can also calculate the average or mean frequency. And this is the formula for measuring the peak frequency and for measuring the average frequency. Okay. In America, if we do the QC measurement of the noise, the peak frequency and average frequency should be included in our report. But in Indonesia, it is not mandatory. The mandatory is only for reporting the noise level, not the frequency maximum, peak frequency or average frequency. Okay. Okay, another parameters, maybe the Nyquist frequency. The Nyquist frequency is the cutoff frequency. And this Nyquist frequency is depend of the size of the pixel. Okay, if we use the smaller pixel, the Nyquist frequency will be higher. Okay, so if we use the very small field of view, meaning that the size of pixel is relatively high, so the Nyquist frequency is relatively high. Okay, okay, this is the Nyquist frequency. And we can see here the NPS for the FPP, filter back projection. And this is the NPS from different tube loading or different MAS. We can see here that if the MES is very low, the noise is high. And if the tube loading is very low, very high, so the noise is lower. And if we normalize all NPS, we can have the NPS like this. All NPS is very close each other. So there is different NPS for different tube loading. It is, we hope, it is our expectation for the filter back projection for different MAS. So the difference is not on the noise texture, the difference only in the noise level, on the noise level. But for the iterative reconstruction, in this example, MBR, model-based iterative reconstruction, this is the result. We have NPS. I think it is common, as we expect. For the very low MAS, the NPS very high, and for high MAS, the NPS is very low. It is our expectation. Okay, but if we normalize these values, we have the curve NPS like this. What can see from this graph? This is very interesting because the peak frequency is shifted. We can see here this one is for NPS normalization for the 5 MPS, and we can see here the peak frequency is the lowest, and for the 300 NPS, the peak in this position. So there is a shift. So in the in the iterative reconstruction, the different MAS will shift the peak frequency. It is very interesting. Yeah. It means that the IR is non-linear reconstruction. It is different from the FPP. The FPP can be called as the linear reconstruction, but the IR is non-linear reconstruction because the different MAS, it should be have the same peak frequency, but in the fact the peak frequency is shifted like this. So the IR is non-idealized system as in the FPP. So the NPS is rotationally invariant. The noise magnitude is inversely proportional to the MAS, and NPS shape is independent. is of the MAS. It is, we can see the more complete picture of the noise. So this is why we important for us not only the noise level but also the peak frequency of the NBS. Okay. And by using the IndoQCT, of course, we can measure the NPS either automatically and manually, and we can set the number of the ROI, we can set the ROI size, we can set the position, and we can set the sampling angle for converting from one dimension to two dimension to one dimension. We can set with the different angle, and we can also use the different detrending, maybe first polynomial or second polynomial and so on. And we can also using the fitting, we can also using the fitting, and we can also measure the NPS from different slices. For example, it is recommended for measuring the NPS not only using one slice, but it is recommended to use more than 10 slices. For example, 100 slices. So the computation will be very, very, very hard, and maybe takes a long time. Okay, this is the example. Using the IndoQCT, we can measure the two-dimensional NPS, and then we also can have one-dimension NPS. Okay, we come to the conclusion. The noise is the most important image quality parameter. The noise level can be simply estimated by measuring ST within homogeneous image. The noise texture can be measured using NPS by Fourier transformation on homogeneous ROI. And the noise texture characterized by the peak frequency and the mean frequency. And in the QCT can be used to measure the noise level, noise homogeneity, and also the NPS. Okay, I think this is all from me. And now we will try to measure the noise using IndoQCT. Please open your IndoQCT. We try together. As usual, double click this button. Okay, our IndoQCT has been opened. And now in this example, we will try to measure the noise using the GE phantom. But actually you can use the different phantom. Okay, and then to measure the noise, we should click the tab number 3, this one. Okay, and then we move in this position. Okay, and in this sub tab we have 4 sub tab: the noise level, uniformity, homogeneity, and NPS. And now the first we will measure the noise level. Okay, this is the example. You can enlarge this one. So this is the module for measuring the noise on the GE phantom. So we close. So we should change this image to the homogeneous one. Again, this is the homogeneous one. Okay, this is the this is the input parameters. This is the result section, and this is the standard, and this is the nodes. For example, the GNI, SD, ROI, GNI is the global noise index, and so on. Okay, now we will try to measure the noise level. Okay, we can use the automatic or using the manual one. If we click the manual one like this, we can choose the type of the ROI type, can be circle, can be square, can be polygon. Okay, in this example, maybe I will choose the square, for example. Square, okay. And then we can choose the ROI size. In this example, default is 40 pixel. Of course, we can choose another size, for example, 60 pixel. And we can choose the slice, single slice or multi slice. If we click the multi slice, we have the range from 1 to, yeah, we can set maybe up to 100 slice, for example. This is the step for the range. Okay, in this example, I choose only single slice because in this example, we have only one slice for the homogeneous slice. Okay, for the manual one, we have one ROI and we click here and we can locate this ROI within the homogeneous region as our design. For example, in this location, and after that we calculate, and then this is our ROI, and then we have these values. The noise is the 5.31 Hounsfield unit. And this noise is from these images, and these images is scanned with the voltage 120, chip loading 200, and slice thickness 5. These values are from the DICOM info. And this one is normalization with the voltage 120, chip loading 300 MAS, and the slice thickness 8 millimeters. And we have the 3.43 like this. And of course, we can save these values. And we can compare to the standard. In this example, because yesterday we set to the IAA standard. And IAA standard for the noise level, there is no standard. Yeah, okay. Okay, like this. Okay. And now we will move to the second parameters for the measuring the noise uniformity like this. Okay, and now we have on also the two options, the automatic one and manual one. In this example, I use the manual. So we have the 5 ROIs as yesterday. So we click number 1. We locate in this location, and number 2 we locate in this location, for example, and number 3 we locate in this location, number 4 we take in this location, and number 5 we take in this location. So you can see here that for the red one should be at the center, and the blue one in the peripheral location. Okay, you can like this. So for the manual one, the location is depend on us. So it is very subjective. Okay, and after that we calculate. This is our ROIs, and then this is our result. This is the pixel the noise values within each ROI from number 1 to number 5, and this one is the uniformity. Uniformity is the maximum values minus by the minimum, and this the estimated noise with the standard values, and we have these values, and the uniformity is the 0.53 like this. And the IAEA said that uniformity should be within 2 Hounsfield unit. And this example, because our result is 0.5, so the result is pass like this. And this is the city number, noise uniformity. Okay, and now we will measure the third one, is the homogeneity. Okay, the homogeneity, we can also automatic one, and we can set the manual one. This example, we use the automatic one. And the threshold, it is the threshold, the section of the phantom, and the kernel size with the 11 pixel, for developing SD map, standard deviation map, in the 11 pixel, and then we make the SD map. We have the limit from -100 to the 100. So by using these values, we only develop the estimate within the outside the phantom, because the pixel value is around 1000. So we will not develop the estimate outside the phantom. Okay, and of course we can change these values. Okay, and the distance ratio, and the default is 85, is we can set compared to the phantom areas. If we set a smaller, so it is away from the border of the phantom. And then we set the cell size. In this example, the 15. It is the cell size on the SD map. Okay, we will try to get. We can calculate with the default setting. Okay, and then we calculate. Okay, and we have three results. This one is the SD map. From this SD map, we can obtain the histogram. As I already mentioned, in the maximum frequency, the SD in this location is around 4, is considered as the global noise index. Okay, so we can see the global noise index is, this one. The global noise index GNI is this one, 4.59, like this. And from this SD map, we have this one, the GNI, the histogram, and from histogram we can obtain the GNI. And from this SD map, and then we make the cell with size of the 15 pixel, like this. We have so many cells here, and then the software will calculate the average within cell, and then we have the maximum one and the minimum one, and the maximum minus the minimum is the noise inhomogeneity. And from the cell, we can also make the calculation of the standard deviation, and the result is the NUI, noise uniformity index. Okay, and we have the result like this. This is our result. Okay, this one. The maximum mean is the 6, around 6, and the minimum mean 3.5. The GNI is the 4.59, and the NUI is 0.47, and the inhomogeneity is the 2.65. And there are no standard for these parameters, because these parameters is relatively new parameter. Okay. Okay, it is the for measuring the noise homogeneity. And now we move to the NPS measurement. NPS measurement. This is for the NPS measurement. We can see in the example. Okay, I like this for the homogeneous one, and this is the ROI within the example. Okay, this is the default setting. We can use the automatic, and of course we can also using the manual one. We can locate the ROI within specific location. This is threshold standard. This is the ROI number. The ROI number can be 1, 2 horizontal, 2 vertical, 3 horizontal, 3 vertical, and the maximum one in the QCT is 9. Okay, maybe in this example we will use the only one like this. Okay, this is the default, and then we calculate the NPS. Yeah, this is the result. This the result of the one dimension NPS. Okay, this one. This is 2-dimension NPS, and this one is the 1-dimension NPS. This is only one ROI. One ROI. Okay, I will close this one. This one. Sorry. This one and this one. And now we will use the different setting. Maybe I use the 9 ROIs. I click this one, 9 ROIs. Okay, and then I calculate again. Yeah, this is the result. We can compare the two dimension. This one using only one ROI, and this one using the 9 ROI. Okay, I think using the more ROIs, the result is better, getting better. Yeah, because many data for developing the NPS. This is for the 2 NPS, and this one is the 1-dimension NPS. This is for the 1 ROI, and this one is for the 9 ROIs. Okay, by using the 9 ROIs, the result is better. Okay, and now we try another setting, but this measurement is only done in the one slice. It is better to measure maybe up to 100 slices. So if we have the 9 ROIs and we set up to 100 slices, so we have a 900 ROIs. I think the result is better. Is better, but the time, of course, is longer. Okay. Okay, and now we will try using this one, using the detrending. Detrending, the default using the average one. So it is no problem if you measure not in the water area. You can also measure in the acrylic area. The important thing, the area should be homogeneous, but the material is not important because we're using the detrending. The default one is the average, so it is not important, the material. You can measure in the water, you can measure in the acrylic and so on. The important thing, the material should be homogeneous. Okay. Okay, I will try using the average, and I calculate this result like this. like this. And now I will try again with the detrending is not average, but using the two second polynomial, the detrending second polynomial, and I calculate this result. Okay, you can compare. This is using the two polynomial, and this one is using average. What is the difference? Yeah, the difference in the lower frequency. Yeah, because if our image has trend, the trend is lower frequency. Okay, lower frequency. By using the detrending with the second polynomial, so the trend is dilated. So the frequency in the lowest frequency is dilated. So we can see the noise in the very low frequency is very low like this because the detrending. Okay. The default one in the QCT is the average, but you can use the different detrending system. But in the QCT we have only three options: the mean, the first polynomial, and second polynomial. If we want to use the different detrending, please develop your own software. And maybe in the next we can also develop the other detrending function. Okay. Okay, and now we will try another example. Okay. Another example. Okay, yeah, I will try on the in this one. I will use the computational phantom because we can change the parameters. Okay, without scanning in the hospital, we can change the parameters only with our computer system in our home. Okay, and now I will make the in this example, because we are studying on the noise, so the spatial resolution I decide to none. So the image is very ideal in terms of the spatial resolution. And now we will try with the NBS. Okay, NBS. Okay, and now we will use this one, the model. And in this example, I think I use the Poisson like, maybe the integral noise, the integral NPS. Okay, the integral NPS theoretically should be similar with the noise level. Okay, the integral noise, it means that all noise on all frequencies should be similar with the noise level. Okay. Okay, we set, for example, in this example, I set to the 15, the noise level is 15. And now I set the target frequency in this example, maybe 5. And we can see the preview of the model. Oh, sorry, this can, yeah, ini sometime because we calculate the fitting, sometimes the fitting is not always success. So we should consider that. I change this one is to maybe 6 maybe, and our preview. And this is the result. So the peak frequency is 0.5. 0.5, and we okay, and we okay, and then okay, please look at this picture carefully, and I click this open button. Yeah, this result. Okay, this result. You can see with the relatively high frequency. Okay, relatively high frequency, and you can measure. You can measure the noise. You can the noise. Okay, yeah, around 14. Yes, similar to the 15. Okay, and you can also measure the NPS. Okay, and now I will change the setting by using this button, and then we get the NPS. And okay, this one I will change. The frequency is not 0.5 but 0 fractional point 1. Okay, and this one maybe 0.2, for example. And this one is the preview of the model. Okay, the peak frequency around 0.1. So the frequency is low compared to the previous one. Okay, okay, and then okay, okay. Please see the change, the appearance of the image with the same noise level, with the same noise level. Okay, and then I click OK. Ah, you can see. And I calculate again the noise level, and I get the result like this. Similar with the previous one, around 14 Hot unit. But the appearance of the image is totally different because of the frequency level. And by using the NPS, we can measure, because we have the model can be added to the image, and after that we can measure from the model image. Okay, the NPS, and then I calculate. Sorry, the NPS 9. Okay, I calculate. This is our result. Our result. Our result. We can see. We can see this. The peak frequency is around 0.1. Okay, similar to the model. Okay. Okay, and now I will try again. This one, yeah, this one, and now we'll try to the manual NPS. Get NPS, and then I set to the to the manual one. This one, and then manual like this. Okay, and then we set, for example, only the frequency 0.0. Maybe I use this one, the magnitude maximum not 40 but maybe 200. Sorry, we click again. This one 100, 200. Okay, this only one frequency. This manual can be set manually 100. And now we will set also around the 02. So we have two frequency. Okay, and then we click OK. Okay, and then okay, I locate in this position. Click OK. This is our image. Okay, our image. And now we will try to measure the NPS. We have to pick. We calculate again. This is our result. We have the two peak of the NPS. Okay. Okay. I think you can change by yourself, and you can also measure, and then you can also use the NPS for measurement to make the computational phantom also. Yeah. Like this. Okay. Please try by yourself. And now it is the two-dimensional NPS with two peaks in the two dimension. Okay, I think enough from me, and we maybe if there any question can be uh, from participant. Please. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much for the explanation, Dr. Khairul Anam. Now we come to the discussion session for all the participants who want to ask the question to Dr. Khairul Anam. You can write on the chat box. We can start from the first question, Dr. Anam. Here is the question from Mr. Ahmad Zaki. When is the parameter such as noise homogeneity and PS clinically required? For example, during the acceptance and the QC processes. As far as I know, determining the noise uniformity value on how evaluating the equipment's reliability based on the patent regulations or uji kesesuaian and the measurement guidelines provided by some manufacturer.
Yeah,
That is the question.
it depends on our country. In Indonesia, we only measure the noise level. But if you in America, for example, you need measure noise level, noise uniformity, noise homogeneity, and also the peak frequency of the noise, and also the average frequency atau mean frequency of the frequency. So it depends on our country, our regulatory body. Indonesia is very simple. Indonesia only the noise level and noise uniformity is enough.
Okay, thank you for the answer. If Mr. Ahmad Zaki, you still have any feedback, you can write on the column chat. We continue to the second question. Here is from Mr. Arif Naufal. For multiple slice NPS, do we need to consider correlated noise between different slices? Is NPS a function of slice?
Yeah. Until now, up to now, we measure the NPS only in the single slice, in the X and Y axis. It is very important to measure the NPS in the Z-axis or in the three-dimensional axis. It is very important. So, but in the QCT, we cannot measure exactly in the three dimension. It is very time consuming. But in the QCT, we can measure in every slices, and then we can average from the three dimensional. Actually, using the IndoQCT, we measure in the two-dimensional, and then we can calculate the average from the Z-axis. But it is very important to make calculation directly from the three-dimensional images. It is important, and I think the latest paper published in the medical physics in the PMP, they use measurement directly from the three-dimensional images.
Okay. And then we continue to the third question, Dr. Anam. Here is from Mr. Wahyu Hutomo. Sir, if during a single scan, we get more than one slices, which contain homogeneous weather area, is it a must to measure noise uniformity and noise accuracy for each of the slice, then averaging this value for all the slices?
Yeah, I already answered this and this question.
Yeah, I
Yeah,
think it's just the same
basically,
answer.
the noise, also the noise uniformity, little bit different in one slice to another. But I think for the QC, it is enough using one slice, or maybe we can average from the 5 slices. But Actually, the image is three-dimensional. So if we want to measure the three-dimensional images, it is better, but it is more difficult.
Okay, Doctor. And the next question from Mr.
And maybe I will show how to measure on the many slices. Okay, please wait
Sure.
a minute.
You
I
can
will
show.
show you to measure the NPS from many slices. Okay. Okay, this is our IndoQCT. And then I open the image. Sorry. And then from GE maybe. From GE. Maybe from Mafre. Maybe this one. Various filters. In the soft tissue. Oh, I don't know. Oh, I think only very small number of using this GA or this one maybe. But this different can rattle. I'm sorry. Please wait a minute. Stuff button.
Yes, sir. We will wait. For all the participants who maybe join in the Zoom or in YouTube, you can write your question in our
Okay.
YouTube channel.
From this one is slide number 21. 21 up to this one around 35. And this one, okay, they're using this multi-slice from 21 to 30, 35 with the slice with the row number 9. So the 9 multiply with the 14 slices. Okay, and calculate. It takes I think this is the result. Yeah, maybe it takes 1 or up to 5 minutes maybe. No, not 5 minutes. Yeah.
Okay. Is there any minimum amount of the slice or the image, Dr. Anam?
Yeah. Yeah. This one.
Is there any minimum
We
amount
have the
of the
result.
image?
This is from
Okay.
14 slices. 14 slices. This is our two-dimensional NPS, and this one is the one-dimensional NPS. The result is very good, very smooth. Yeah, because we have no. The minimum slice is one slice. We can measure the NPS on one slice. Okay. Yeah.
Okay.
Yeah.
Any addition?
Yeah, enough.
Okay, we move to the question from the YouTube channel from Physics QIA. What is the difference between threshold and limit in homogeneity subparameter?
Threshold. Yeah, sorry. This one. This one, the threshold is for automatic detection of the phantom. And then the limit in the uniformity. And I think in this one, the threshold is for the detection of the phantom, and the limit is for this is the border for making the noise map. For example, if I set this one, maybe from maybe from 1,500 like this. This one is less than the area of air, okay? Because the air is minus 1,000. And we set to the minus 1,500. Okay, and now we calculate. Yeah, this is the result. You can see. So our noise map is within all images. Yeah, including within the area, the air area. This is the limit, because we set the lower limit is minus 1,500. Okay, like this. So the limit is for the developing the noise map, and the threshold is for detecting the phantom. Okay.
Okay, thank you for the answer, Dr. Anam. We continue the question from Mr. Amos Toka. Is there a standard ROI number for NPS measurement or optional for study purposes?
Yeah, it is optional. Yeah, if you use the more ROIs, it is better. And many studies using the different location. I think in the medical physics, they use the three-dimensional ROIs and using the circular position, and then he locate in the different location. So many technique to make the ROI. Basically, there is no standard, but using more ROIs, it is better. But using only one ROI is enough, of course. Tutup ya.
I think there is, okay, Mr. TS.
Okay, I'm sorry for the trouble of the connection. The
Yeah.
next question is from Mr. Arich. Okay, the question from Mr. Arich, is it possible to measure the NPS directly from clinical patient image? Will the NPS results be different from measurement on homogeneous phantom?
Yeah, it
Please,
is,
Dr.
I
Anand.
think, the challenge to measure the NPS directly from the patient images. And now, many researchers have tried to measure NPS from the patient images, and they search in the most homogeneous one. Yeah, but still facing many challenges. So and now the trend is to measure the image quality directly from the patient, noise from the patient, spatial resolution from the patient, NPS from the patient. It is already started, but still facing many challenges. Okay, it is very nice if you develop the algorithm to measure the NPS in the patient images. I think if you can overcome the challenges, it is publishable in the medical physics journal, I think. Yeah.
Well, thank you, Dr. Anand, for the answer. And then the next question is from Miss Mega. I would like to know if I am able to do a mini project on IndoQCT, like I saw many papers published by your team on IndoQCT. I am thinking of not publishing a paper, but at least do a small project based on one of your published paper. Will I able to do it with your support and guidance, Dr.
Yeah,
Anand?
yes, please do. And if you have any problem or you need guidance, please send email to me. Inshallah, we will answer. Yeah.
Thank you. So we are open to collaboration, right, Dr. Anand? And then the next question from Mr. Wahyu Hutomo, just to confirm, sir, threshold of -100 means that the system will not detect and process any pixel whose value below that number.
Yes,
Is
right.
that true?
Yeah, right.
Okay. Okay. Oh, thank you. Okay. Is there any feedback from all the questionnaire? You can write your feedback on the column, on the chat column, or
Yeah,
for
yeah.
those who following the YouTube, you can also give the feedback over there. Or maybe anyone want to ask directly to Dr. Anam?
Yes, I want to.
Okay, Miss Rizka Amelia, please.
Okay. Thank you, Dr. Anam, for the wonderful presentation. I want to ask about the NPS. So if we talk about NPS, we talk about the noise texture. So which one is better? If we have the NPS with the peak frequency that high or low, which is the better one? And the second one is, since the noise texture that you have explained is very important in the city imaging, is there any possibility to use the NPS or noise inhomogeneity to be the metrics for QC in the near future?
Yeah. It is for the second question, it's depend on the regulatory body. In Indonesia, based on then. So if we use, for example, the NPS as the metric for the image quality, we should educate the medical physicists in the hospital. Yeah, but it depends on the patent or the regulation. But it is, I think, in Indonesia maybe we need longer time. But in America now, we need not only the noise level, but also the NPS should be measured in the from the clinical image from the hospital. Okay, this is the second question, and from the one question about the what is the better, the low frequency or high frequency. It is not about the what is the better, because the algorithm and the reconstruction algorithm produce the different noise texture. Yeah. Commonly, the soft kernel produce very low frequency, and the bone kernel or the edge kernel produce very high frequency, and the appearance in the image is totally different. So it is important for us in the clinical setting to decide what is the maximum value, what is the optimum for the peak frequency for specific clinical task. I think, for example, for detecting nodule in our heart and for detecting the cancer within the soft tissue, I think the frequency for the optimum appearance is different. Okay, it is important to do this research, and I will explain this when we discuss about the detectability index D prime, maybe in the next week. What is the effect on the frequency on the detectability index? Okay. And now we don't have any information, but for the detecting the nodule, what is the what is the optimum frequency? We don't know. We don't have any information about this. So it is the new field for the research, I think. Yeah.
Is there any feedback from Ms. Rizka, maybe? Or you are satisfied
Yes,
enough?
there's a feedback,
Okay.
Miss.
Please.
If we talk about the deciding the reconstruction kernel for having a optimum frequency for detection, we as medical physicists, we don't have any role since the imaging the patient is being the task of the radiographer. So is it important to us to collaborate with the radiographer if we talk about how to get the good image and regarding about the good noise texture to detect the noise and also increase the diagnostic performance.
Okay, thank you. It is very interesting question. Yeah, of course, we should collaborate the medical physicists, radiographers, and also radiologists. The medical physicists with the radiologists, they has the responsibility to produce the optimum protocol, and the protocol then will be used by the radiographer to make scanning to the patient. So I think the responsibility of the medical physicist to make the optimum protocol for specific tasks is very important. Again, and by using our knowledge about the noise texture, NPS, detectability index, it is very important for creating the optimum protocol. And then after we decide the optimum protocol, the radiographer will use this protocol to scan the patient optimally. So it is, I think, very important task, and we should collaborate with medical physicists, radiographer, and also radiologists.
Okay, that is the very clear answer, I think. Ms. Rizka, are you satisfied enough? Okay, I think there is no feedback. We'll come back to the question from the YouTube, Dr. Anam. There is a feedback from Physics QIA. In NPS, can you explain about sampling degree and option, where in option there are original and fit and both?
Yeah. This one. Full screen. This one. Sorry. This one, the degree, this one. And this one is degree. Yeah, this one is the sampling degree. It is for converting from two-dimensional NPS to one-dimensional NPS. For example, if we choose, for example, 90 degree. So for averaging, we only have 5 profile. Yeah, so 0 degree, 90 degree, 180 degree, 270 degree. If we set 90 degree. But if we set to the 1 degree, meaning that to make the averaging, the profile is rotated every 1 degree. So we have around 360 degree in one rotation. So it's better to use the smaller degree is better, but the computation time is longer, of course.
Okay. Is there any addition, Dr. Anam, or is that enough?
I think enough.
Yeah. Okay. We have 4 minutes left. Maybe the last question from me, Dr. Anam. I really want to know about the noise level that we have measured by many techniques here. Can us analyze which one of, you have mentioned that the noise came from many factors such as quantum noise, image generation, and system limitation. After we measure the noise level, can us analyze which one of those three factors is the give the most contribution to the noise level, or it's just the average from those three factors, Doctor?
Yeah. If we measure, for example, using the 1ROI, we capture the total noise from three sources, from the quantum noise, the system limitation, and from the reconstruction system. So we can spread it at all. But if we do the specific study, so we can isolate the noise only, for example, from the system limitation. So it is, but we use many data to isolate only from one source. But if we measure in 1ROI, actually we capture total noise from all sources.
That's very interesting discussion, I think, but our time is limited, Dr. Anam and all of the participants. We have already come to 11:40, almost 11:40. So to close this session, maybe Dr. Anam, you want to give a closing statement for this day, for this session?
Yeah. Today we have studied about the NBS, and in the afternoon after Jum'ah prayer we will discuss about the MTF. It is also very important with Dr. Nurdiana Usman. Please join us again to learn about the MTF.
Okay, thank you very much, Dr. Khairul Anam and all of the participants. We have to come at the end of the first session for today's summer course. We will continue after Jum'ah prayer at 1 p.m. and we will continue the topic with Dr. Nurdiana Usman. And so please stay tuned with us in this summer course and let's have a short break. Thank you, everyone, and thank you, Dr. Khairul Anam, and good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. See you again. Okay.
See you again.
Ya, Assalamualaikum warahmatullahi wabarakatuh.